Okay, first thing I want to say, thank you, Pablo, for organizing this nice workshop. So I'm glad to be here to present our last work in resistive switching. I'm working at the University of Buenos Aires, and usually my main topic of research is related to high pressure effects on different phase transition. So we have a head of the physics department that said that he has a rule. He said that for the physicists, he said that in different ways you always came back to your PhD subject. So as I made my PhD in the late 80s, I worked at that time on high-TC superconductors. So here I came back to the subject in a certain way. So I'm working. This is the work essentially of with many collaborators, with Alejandro Schulman. This is his PhD thesis. I'm working also with closely with Marcelo, and in early moments also we have fruitful discussions with Pablo, Ruben Huet, and Maria Jose. So this is the outline of my talk. I will show you different characteristics, or the characteristics of the switching in YBCO and metal junctions, and how we can use we can make a model to understand the typical characteristic of this switching, and I will show you how we can use superconductivity as a probe just to understand which is the mechanism behind this switching. And then after that, I will talk about the retentivity on this type of samples. Okay. So why we want to analyze and to study the retentivity? Well, first, because this is one of the most basic properties of a memory. You want that the memory keeps the information for a long time period. So there are many good achievements of retention of over more than 10 years in some cases. But our approach to this is not this one. We want to use the bad retentivity just to try to understand what is the mechanism and the physics behind these switching properties of this type of systems. So we choose a good ceramic YBCO sample, well oxygenated, with a nice superconducting transition, with a standard width of the transition, and with good critical or currents. So in this type of samples, we make this type of contacts. We have a sputtered gold or platinum. These are, in general, handmade contacts. We use silver paint in most of the cases. And we use this type of circuits just to study what happened with we apply a pulse and then a bias. This is the set, and we read what happened. We can measure different voltage just to see which is the resistance of one of the contacts, or which is the resistance of the bulk sample or the other contact. And sometimes we also use this type of circuit just to study the IV characteristics of this type of samples. So this is one of our first studies of the resistive switching in this type of samples. You can see here the resistance as a function of time when we apply a different number of pulses, and what you observe here is that you have a noisy behavior with a number of pulses first, then you have a clear decrease, but you also observe some relaxation that is, in this case, most probably related with overheating of the sample. Then you observe this long relaxation to a lower level of resistance, so you are observing this type of resistive switching in this sample. Here you have a measurement applying pulses, 30 microseconds pulses, and you can observe this two-step process of the resistive switching. You observe this noisy reduction of the resistance, and then a sudden decrease, something like an avalanche or some percolation in some part of the sample. So here I show you the IV characteristics applying a triangular waveform of something with a period of 0.1 millisecond, this type of waveform. So I'm showing here the IV characteristic of one of the contacts and the other contacts, the two contacts involved in the pulses. And what you observe is the type of non-linear IV curves with they are of the crossing types, and this is a bipolar behavior. And if you look at this, you zoom this part, you can observe that you have a progressive change in resistance with each cycle, similar to what I showed you before. And for example, if you plot the resistance as a function of the current, you observe that the contact that is has a lower resistance than the other doesn't change to match its resistance. You have this non-linear behavior, and then in a certain moment you observe a sudden change of the resistance, something like I tell you is related maybe to a percolation or to an avalanche. If we look again to this, what we observe is that you can say that you have the high resistance of the same contact and then the low resistance each time you make this cycle. And what you observe is that with each cycle you have an evolution of the high resistance state and the low resistance state of the same contact. So I think this is not a simple problem, and this is general. If you want to understand the physics, this is a diffusion problem with what is important is the local concentration, probably, so you can observe this evolution with time. We analyze during this type of cycles the differential resistance. For example, here we have two cycles. Of one of the contact, we begin with this high resistance state. Then you observe that you are following a certain path here, and then when you again are with a small current, you observe that you are in the low resistance state here. Then you make another cycle, you are again in the high resistance state. So this is the bipolar behavior. But when you do the second cycle, you observe that you are obtaining a lower low resistance state. So you observe this progressive reduction of the resistance in one of the contacts. And what we have done is try to model this with a simple circuit, just to try to understand what is happening during this cycle. This is the equation of this circuit. And what we managed to do is to fit all of one of the branches here. For example, this is the high resistance. And we managed to fit all this curve with constant values for the diodes, for the characteristic properties of these diodes, so the reverse current, for example. And this is also the resistance of an interface and the resistance of the bulk. So fixing all these values, we managed to reproduce all this curve. But when we want to reproduce the second part of the curve, when you are decreasing the current, then we have to change all these parameters. So when we apply this pulse, this positive pulse, we are increasing the metallicity of these diodes, and then we are reducing this interface resistance and increasing the bulk resistance. But we managed to fit, again, all this branch using constant parameters. So this is telling, I think, that we can observe the very moment of the switching in the sample, and the very moment occurs just in this region, okay? Because all the other part, you can express it and you can obtain it in a simple model with constant parameters. It's just the different portions of the curve, and just to compare. This is the high resistance state and then the low resistance state, okay? And then what we fit it, okay? The fitting values. So with all these experiments, we knew that we have to apply a large number of pulses just to obtain a reliable result. So in general, we apply something like 1,000 or 2,000 pulses. It's not very interesting from the commercial point of view or a technological point of view, but with this type of protocols, we managed to obtain a clear switching from a high and to a low resistance state for both contacts, and we observe this typical resistance hysteresis switching loops with one of the contacts in the high and then in the low, and then the complementary behavior for the other contact. So we also perform this at different temperatures, and what we observe is that as we increase the temperature, the amplitude of this hysteresis switching loop decreases. So, and at certain temperature, this is very low, and the effect disappears. Another interesting thing is that you can see what is the evolution of the resistance of one of the contact with the increase in the number of pulses. So each pulse here is a set of 2,000 pulses, for example, and we apply pulses of the same amplitude, and you can see the evolution of the resistance. This is a logarithm evolution with the number of pulses that you are applying, and you can say, for example, well, I want to know which is the number of pulses that I need to obtain a certain resistance, and so you can make this plot. This is the pulse, the voltage of the pulse that you apply as a function of the number of cycles to reach that resistance. So something like the number of pulses to failure. You can think about this in this way. So this is very similar to happens in a metal when you are applying these strain stress studies. So you are looking at the endurance of the metal. You are making an oscillatory stress to the metal, and then you manage to obtain a failure. This is a fatigue experiment. So we think that here there is also a physics very similar to this, similar physics to in this type of when you are pushing this vacancy. So there is very similar to the fatigue experiments in metal. So you are moving the effects in one case, and here you are also moving the oxygen vacancy. So we think this is a very similar physics that is interesting to follow. Here I can show you also the transport properties. Here we have the resistance of the contacts as a function of temperature. So you can follow the resistance of the contact that is in the low resistance state, and here is the other contact that is in the high resistance state. And what is interesting is that this contact is metallic, and you can see the superconducting transition of YBCO there. But the fact is that here you are not looking at the 4-terminal or the bulk resistance, because the bulk resistance of YBCO is very small compared with the resistance of each contact. So here what you are looking is to a small filament of the superconducting filament, so you can observe a big drop of resistance, because this is related to a very large geometrical factor of a filament near one of the electrodes. So if you apply a severe pulsing treatment, then this contact that was metallic then becomes semiconducting, while the other one comes to a more metallic behavior, and then again, here you observe the superconducting transition, while in the other one you now are not able to observe this. So we can broke and restore the superconducting zone near the contacts by pulsing here. And this was also observed by some experiments here by Mariano Quintero and from Pablo's group, where this is manganite, and you can observe the resistance of the manganite. And when you look at the resistance of one of the contacts, you are able to observe also the same insulator to metal transitions, and that you were not be able to observe if you are only measuring the contact. So this is not the part in series of the sample, because this is only a small contribution. So again, here with the pulsing, you are observing the contribution of a filament near the contact. So you are able to observe the same thing of the bulk sample there. What happened in our samples? We think this is something special in YBCO, that you can also observe changes in the bulk of the sample. So I'm saying that we are applying pulses and you are obtaining changes in the resistance in millimeter size. So you are not only changing the resistance very near the interface, but you are also propagating these effects to the bulk sample. And this is very, very clear also. This is a change of something like a 3% in the resistance. And that is interesting. Here you can observe the superconducting transition. That is mainly this is a transition of a granular sample. So you have the onset related to the onset of superconductivity in the grains. And then here there is this width of this transition is related to the Josephson junctions between the grain boundaries. So when we apply a severe pulsing treatment here, we have 10 million pulses that we apply. We managed to increase the width of the transition. We didn't change the onset of superconductivity. And what is very interesting is that we prevent the percolation of superconductivity. So we have not only changed the resistance 1 millimeter away from the contacts, but also in the whole area of conduction of the sample. Okay? And then when we apply the pulses of the opposite polarity, we managed to recover partially the superconducting transition. Okay? But then it was not possible to recover it again like in the pristine sample. If we look at the resistance hysteresis switching loop, you can observe the evolution of the resistance of one contact here for different temperatures. And you can see when you increase the temperature how the loop has now a lower amplitude. The same happens with the resistance of the other contact, and then you can see the resistance of the two-terminal device, and you obtain this typical table with legs shape of the curves. So what is interesting is that here you can observe that there are some relaxation effects that the system wants to go to its previous state, its previous resistance state. You can observe it here. You have the evolution of the resistance to low resistance. You want the pulses increases the resistance and then it evolves to a lower resistance. And here you have the opposite behavior. This was also observed in this in PCMO and metal devices, but this the group of Ignatieff, where the same type of relaxations were observed, and this was interpreted as an oxygen diffusion evidence of that is at the origin of the resistive switching. And you can observe here this relaxation of the resistance after applying the pulses. And making some math, you can try to relate this evolution of the resistance with the diffusivity, the diffusion of the oxygen in this case, in this type of oxide, and then you can plot here the logarithm of the slope of this z function and obtain the diffusivity constant. Okay, so you can obtain this law, this expected law. This is very mathematically dependent of how you choose the first resistance and the second one. We check what happened with our measurements. Okay, here I can show you this resistance, the evolution of the resistance with time after applying pulses. So here you apply a pulse, and then you wait, and you can observe a little overheating in the first 10 seconds, but then after that, for many hours, you can observe the evolution of the resistance. So you have this anomalous, I would say, anomalous relaxation effects. This is clearly not an overheating problem because this is the temperature dependence of the resistance of each contact, and you can see that these contacts are semiconducting-like. So if you heat it and then the contact cool down, you will always observe a reduction of resistance. So, but here you can observe that the resistance relaxes to a higher value. So this is an intrinsic relaxation, not not related to, only related to overheating. And you can observe here the relaxations. And if we do some mathematics, like using, this is the RRAM equation used to describe the evolution of the transition of when you are getting a new sample at a fixed temperature, you're analyzing what happened with the increase of one phase over the other, and you can make this mathematics. You call this this is the relative evolution of the resistance, and you can propose this type of dependence with time. And if you make more mathematics, you can linearize, and then from the slope of this, you obtain information about the exponent n, and from the intercept here, you can obtain information about the characteristic time. So we have performed these resistance relaxation studies at different temperatures for many hours, and you observe that we obtain this linear dependence of y on the logarithm of the time. So that is a good description of our experimental data. And what is very interesting is that we obtain the same n exponent for all the temperatures. So this exponent is not temperature dependent. And for all the relaxation, we obtain similarly the same exponent. Here, if you apply a convenient shift, you can see that most of the curves fall in the same line, so that you have this evolution is you obtain always parallel curves here. Just to check if this is not only proper of YBCO junction, we have performed the same experiment in a manganate device, and we obtain nearly the same effect, that this linear dependence of y with the logarithm of time. And I'm saying that this is anomalous diffusion because if this is a thermal activated process, you will wait that the characteristic time should decrease with temperature because everything comes quick now, because it's easier. But what we observe is that the characteristic time increases with temperature at a fixed power. This is the power of the applied pulses. And then also, if you fix the temperature and you increase the power of applied pulses, you also obtain an increase of this characteristic time. So this is just to check also, we obtain the same result in a manganate device. So this is not, in principle, included in the model described by Maria and Marcelo, because this was discussed, I think, yesterday. This is a steady state model. So something new is needed to describe this time evolution. And we were just thinking that this is probably more associated with the problem of a particle diffusion in a sea of traps, because when you apply a pulsing treatment and you increase, for example, the oxygen concentration of the sample near one of the contacts, then this concentration is not in the equilibrium value, then you have a diffusion. But this diffusion, if you have oxygen diffusion in interstitial positions, or this is in grain boundaries, you will only have a change in the resistance when this oxygen will be trapped. So you can think that the problem is related to a survival probability, and the survival probability can be expressed like this. This is associated, is proportional to this exponential, where here you have the time, D is the dimensionality of the problem, D is the diffusion constant, and rho is the quantity of traps, the density of traps. So making simple mathematics, we can associate this, the resistance that we are measuring, that is proportional in principle to the density of vacancies, and then you can express the relative change of the resistance as you obtain. This is the X function that we use to plot our data, and this X function will be proportional to 1 minus P. So again, we find that our description of the relaxation that was with this function X will be related to the probability of survival of these particles diffusion in a series of traps, and then we can obtain some information about the parameters that we obtain. So as we obtain an n equals to 0.5, this is, considering this model, this is telling us that the dimension is 2. So this is a two-dimensional diffusion. And I think this is not very strange because you are dealing with a ceramic sample. So we have a lot of boundaries here. And in this temperature range, the diffusion of oxygen is only associated with grain boundaries, because you cannot have diffusion in this temperature range that is near room temperature or below room temperature in the bulk of this sample. So you need more temperature for that. So it's reasonable to have only oxygen diffusing in between the grains. And if you look at the linear dependence of the characteristic time, while looking at this dependence, what you can say is that the density of effective traps is decreasing with temperature. And well, we think this is not. We can think that this also is reasonable because there were measurements on the oxygen diffusion, but internal friction measurements that show that there is some distribution of the activation energy. So you can think that at higher, as you increase the temperature, then you have less effective traps. So as you are reducing the number of traps, so you have the probability to survive of this particle is longer, and then you will have long relaxation times. Okay. So I arrive at the summary. Well, I have shown you the particular properties of switching in YBCO with the IV curves, and using a simple model, a circuit model. We can say that we know when happens the very moment of the resistive switching. And well, I have shown you a particular evolution of the remnant state, a relaxation, that we can interpret as is a relaxation related to the diffusion of oxygens in a two-dimensional space related to grain boundaries. And the evolution with temperature also of the characteristic time should be associated with the reduction of the effective number of traps. Okay, thank you for your attention.
Thank you very much, Charlie. We have some questions.
So I have a question concerning the last point with the diffusion of oxygen. So is there anything known about oxygen interstitials in YBCO? For example, for strontium titanide, it's clear that they do not exist because it's such a compact perovskite structure. For strontium titanide, it's well known that it does not exist. I don't know about YBCO.
Well, in YBCO, it's not also the most usual way of diffusion, but I think this is probably because we have here diffusion in grain boundaries. So I think this is. We know also that when you are we apply the pulses. When I show you the resistive transition, superconducting transition, we change the width of the transition. So probably all the oxygen we are moving is located at the grain boundary. So I think this is a diffusion there. So okay, we can have voids or something like that.
Voids, real
yeah.
Voids. Okay.
So, other?
So the experiment on YBCO were done on polycrystalline samples?
Yes.
Did you try also crystals?
No, we are trying on films, but these are also polycrystalline films. So this is one of ideas, so we are working on that, but we haven't done the experiments yet.
If you look at what was done in group of VASA on STO, if you apply a voltage, you are able to grow filament through the crystal. Do you think it could happen also in YBCO, and that you could find a percolative superconductivity?
I think it's possible. It depends on how easy this oxygen moves in the bulk sample. Here, I have shown you the results in ceramic samples, so I think here the diffusion is easier. Yeah. But I think it's possible to increase the voltage and then try to observe that. Yeah.
Would be interesting. Thanks.
Oh.
Only one question. I mean, you are considering the change in the diffusion coefficient with temperature.
Yes. Mm-hmm.
And from this proposal, you are considering it's not anomalous diffusion. It's the usual diffusion. You have the it's not anomalous. I mean, in a way that the dependence with the effective length, like the square of the diffusion coefficient times the time.
Okay, the diffusion is not anomalous. What I want to mean with anomalous is that you are having a diffusion of oxygen, but that the number of trapping centers depends on temperature. So this is not unusual. You're not usually you are thinking that you have a diffusion that should increase with temperature, and because the diffusion coefficient is going to a higher values. No?
Okay.
Charly, you showed that the relaxation time increases with temperature. On the other hand, you showed that the hysteresis decreases with temperature. Do you see a contradiction in that?
No, because this depends. I think that the amplitude depends on the number of the resistance state of each contact, and these contacts are semiconducting-like, and we saw that these contacts at higher temperatures come to the same resistance. So I think that when you apply the pulses, you migrate these vacancies for the oxygen, but then the diffusion is also high, and you did not retain this unbalance of oxygen concentration.
Other?
When you mention the traps, what do you have in your mind about the traps?
Traps for the oxygens are vacancies.
But where? In the boundaries of the grains?
In the boundaries of the grains, yes, in this case.
Okay, thank you.
So it's actually more a comment from his question. In zinc oxides varistors, you are actually able to follow regulation path after a threshold voltage. And you are able to see that normally they go through grain boundaries, but there's also some path in the bulk, even in bulk materials as well. And you can even follow that because there's light emission. We were doing some stuff like that. So in principle, it may be possible here as well.
I think we have the last question. No?
Sorry. I was talking with you about what he said about varistors.
Okay, so the last question. Thank you very much, Charly.